Bismillahirrahmanirrahim. Our topic is continued. That is, we are doing polyphase systems problem. That is numericals. So in this circuit, we have a star connection source and a star connection load. As you can see, the figure is clear, and the source voltages are 110 0 degree, 110 minus 120, and 110 minus 240. The phase sequences A, B, and C. Remember, the lowercase is used for source, and uppercase, that is A, B, C, uppercase is used for loads. Lowercase for source and uppercase for load. And we have a line impedance, that is 5 minus j2 ohms across each line A, line B, line C. And we have load impedance across each load, that is 10 plus j8 ohms, 10 plus j8 ohms, 10 plus j8 ohms. So determine the total average power. We have to find the total average power, reactive power, the reactive power, and complex power at source and load. Complex power at source and load. So first of all, just recall what was your active power is, what was reactive power, what was apparent power, that is complex power S. Apparent power, complex power in terms of S. So just recall previous formulas. The average power, the total power is expressed in kilowatts. The reactive power is expressed in kilovolt ampere reactive, and apparent power is expressed in kilovolts amperes. So now let's start working on this problem. So remember, this one is important reason for using a three-phase system to generate and distribute power. We'll back into another reason for later. So it is sufficient to consider one phase as a system is balanced, because this one is balanced system. So it is sufficient to consider only one phase. What happening in any phase is happening in all the phases actually. So let's start the solution. The voltage phase voltage, that is which is given to us, which is nothing but 110 degrees, 110 volts, 0 degrees. The unit is volts, right? So because it is a star connection and it is balanced system, it is a star connection and it is balanced system. So we know that line currents equals phase current. So the phase voltage is given to us, and the line current can be found, okay, or phase current can be found. How we can found? First of all, we can find the phase impedance. What is phase impedance? So phase impedance, you need to sum the impedance, that is the line impedance 5 minus j2 ohms plus the load impedance j plus 10 plus j8 ohms. It comes out to be 15 plus j6 ohms. And when you convert it into the phasor form, it will comes out to be 16.15 angle 21.8 degrees. So this one is Z phase, that is the phase impedance, sum of line impedance and load impedance, total impedance, that is phase impedance. So what is phase current? Just by using Ohm's law, current is a ratio of voltage over impedance, that is phase voltage over phase impedance. You can write PH as a phase. So phase voltage over phase impedance, right? So phase voltage is given in this problem, which is 110 0 degrees. Z phase just we found from here. The impedance, the phase impedance, it was comes out to be 6 point, sorry, 16.15 angle 21.8 degree. So what is phase current? That is IPH is equals to, the phase current comes out to be 6.81 angle minus 21.8. See, the this angle is in division. When it comes to this denominator, when it comes to numerator, it becomes negative, and magnitude is divided by magnitude. So you get the phase current. So after finding the phase current, move towards the source complex power, which is supplied by the source. Complex power means apparent power, right? It denoted by S. The unit of complex power are kilovolts amperes. So complex power, which is denoted by S. SS means complex power of source. Complex power source equals, because it is three phase, so it is equals to minus 3 because it is generated by the source, times voltage phase times current phase conjugate, right? So just put the values, and you will get it. So the values was 110 0 degree voltage value, the current value was 6.81 angle 21.8 degrees minus, because it is conjugate, so you remove the minus sign, right? You know how to take the conjugate. When you take the conjugate, the complex quantity, the current becomes, if it was originally negative, it becomes positive. It was positive then originally, then it comes negative, because the current angle was negative, but we take conjugate, so it becomes positive, right? So after solving, you will get minus 2247 angle 21.8 degree, and if you convert this into rectangular form, you will get 2087 plus j 834.6. The unit are volts amperes, because it is complex power. So if you see in this complex power, this part shows to you the real power, and this one is reactive power, right? So the real average power supplied is nothing but minus 2087 watt, and the reactive power is minus 834.6 volt ampere reactive. Now at the load, the complex power absorbed, this power is calculated at source. Now at the load, the complex power is absorbed, because load absorbed the power. So what is it? How we calculate? Just we denote this one is SL. SL means complex power absorbed by load. Complex power generated by source. So complex power absorbed by load is what? Is against 3, that is three phase system. IP, magnitude of the current square, times ZP. How? Because see, the complex power is VI. So we know that complex power is nothing but the product of voltage into current, that is volts amperes, and we know voltage is equals to current times impedance. So finally the power becomes I square Z. So in terms we calculate SL, that is load, power absorbed by load is 3 times phase current squares times phase impedance. So what was the phase impedance? ZP. The phase impedance we calculate already. It was it was given to us, the phase impedance of the load. In this we consider only phase impedance of the load, not the not the line, right? So only consideration of phase impedance of load. So if you convert it into phasor form, you will get 12.81. And because it is balanced star connection, so I phase is equals to I line, and it was calculated earlier. It was calculated 6.81 minus 21.8 degrees. So when you put the values, you will get the answer, that is the power absorbed by load is equals to 3 times the phase current square 6.81, the current magnitude square, times impedance 12.81, 38.66, 38.66. So your power absorbed becomes 1782, 38.66 degrees. And if you convert into its rectangular form, you got 1392, that is the active power, plus the reactive power, that is reactive power J triple one three. So the unit of whole is volts ampere, because complex power, apparent power, I have told earlier also, the units are volts amperes, product of voltage into current. So if you see, the real power from absorbed by the load is 1392 watts, and the reactive power absorbed by load is 1113 volts amperes. The difference between the two complex power is absorbed by the line impedance, right? The difference of the two powers is absorbed by the line impedance, because source minus load, you get line, right? If you it's very simple. If you minus source power minus load power, you get line power, right? Or you can say the source power plus line power is equals to load power, right? Because these some of these two powers goes to load actually. So finally we comes towards the calculation of our power, that is complex power of line, right? See, small l is used for line, right? Capital L is used for load, S is used for source. So keep remember these. So line complex power is nothing but thrice of phase current, or line current, because star balance star connection, line current and phase current being same, times line impedance. See, it times line impedance. In that in the load case, it was times load impedance. Now it's line impedance, ZL, and just put the values. We know that the current was 6.81, the current magnitude, and the line impedance was 5 minus J2. So when you solve this, you will get 695.6 minus J 278 to 278.3 volts ampere. Again, complex power, because it is measured in volts ampere. So the units are volts ampere. So if you want to verify, you can sum up all the complex power, that is complex power generated by source, complex power absorbed by line, complex power absorbed by load. What you will get? You will get zero. When you sum up all the powers, you will get zero. You can verify this, right? Let's move on to the next problem. A three-phase motor can be regulated as a balanced Y load. The three-phase motor draws 5.6. That is, the three-phase motor draws 5.6 kilowatt. What is this? This is active power. When the line voltage is 220, and the line current is line current IL. line current is equals 18.2 amperes. 18.2 amperes. Determine the power factor of the motor. You have to find the power factor of the motor. So recall the formula of the complex power. It was nothing but under root 3 line voltage times line current. See, the apparent power it is measured in volts ampere. No need to multiply by cos. When you multiply it by cos, you will get active power. When you multiply it by sine, you will get reactive power. So here we are going to calculate apparent power. What total apparent power draws by the motor. So all the information is given to us. Line voltage is given, line current is given, right? Just put the values, you will get your apparent power, which is comes from the which draws by the motor 6935.13 volt amperes. Okay, so we know from our knowledge, previous knowledge, that power factor, that is cos phi equals to, it is a ratio of active power over apparent power, right? Cosine phi is the ratio of active power over apparent power. So if you rearrange this formula, you will get P is equals to S times cos of phi. So you know this, you can find power factor. So, right? So you just formula, rearrange the formula. The cos phi equals P times S, and P times S. P means active power 5600. Active power, it was given this 5.6 kilowatt, it was given to us. Active power, and the ratio of apparent power. Just we calculate the apparent power. So divide it, 6935.13, and it comes out to be 0.8075. What does it mean? It means the motor is utilizing 80% of this power. This is apparent power supplied by the source. This is active power utilized by the load. So 80% power is utilized by the motor. This is the meaning of power factor. Three balanced loads are connected on 240 kilovolts RMS. The given information, first of all, write the data of this problem. Three balanced loads are connected to a 240 kV. Remember, when the quantities, sorry, I forget the mic. And in this problem, the two balanced loads are connected to a 240 kV RMS. So remember, the quantities are given to us are line voltages, and line voltages are RMS voltages. 60 hertz, that is frequency, 60 hertz frequency, as shown in the figure. Load 1, there are two loads, balanced load. These loads are balanced and they are connected to the three-phase system, right? So the load 1 draws 30 kilowatt at a power factor of 0.6 lagging. Load 1 draws 30 kilowatt at power factor 0.6 lagging. The term lagging means inductive load, right? While load 2 draws 45 load 2 draws 45 kilovolt ampere reactive. What this means? Reactive power given to you at power factor of 0.8, at power factor of 0.8 lagging. Assuming the ABC sequence, the sequence is A, B, C, the positive phase sequence. Assuming the phase sequence is ABC, find part A, the complex real and reactive powers absorbed by the combined load. What is part A? The complex real and reactive powers, the complex real and reactive powers absorbed by the combined load. So complex power is denoted by S, complex real and reactive power, right? You have to find complex real and real power for load 1. And similarly in part B, the line currents, you have to find the line currents. Line currents. So, according to given information, we have the power factor of load 1, that is 0.6 lagging. So, power factor is what? Cosine. So, you can calculate this phi angle by taking cos inverse of this value. And when you get this phi 1, that is angle, you take the sine of that angle, you will get 0.8. So, we know that the power factor is the ratio of active power over apparent power, and if you rearrange this formula, S equals to P times cos of phi. So thus rearrange this formula, and you will get the power uh, power by power absorbed by first load. So power absorbed by first load is what? P1, let's say P1, and this one is cos phi 1, that is active power by load 1 and the power factor of load 1. So this one is S1, apparent power or complex power. So when you put the values, that is 30 kilowatt and 0.6, you will get 50 kVA. 50 kVA. The value is 50 kVA. So what is the reactive power absorbed by the source? That is the reactive power. It is represented by Q1, because one subscript used for load 1 and two subscript used for load 2. So we are calculating load 1. So Q1 is equals to S1 times sine phi 1. Right? It is also obvious from the ratio that is Q over S is equals to sine of phi. Right? Perpendicular upon. If you recall the triangle, you will get this sine relation also. It is a ratio of reactive power over apparent power. It was changed, right? Power factor was the ratio of active power over apparent power, but sine is the ratio of reactive power over apparent power. So q1 q1 equals s1 psi 1. So what is s1? We have just calculated 50. We have just calculated s1 was 50. And what is sine phi 1? It was also calculated, it was 0.8. So it comes out to be 40 kVAR, kilovolt ampere reactive, right? The reactive power from the source, from the load, sorry, Q1. Thus the complex power due to load 1. So what is the total complex power from the load 1 is nothing but P1 plus of J Q1. That is the sum of active power plus apparent power. Total complex power from the load. So 30 plus J of 40, and the units are kVA, kilovolts ampere, right? Because this one is complex power, that is apparent power, right? So units are kilovolts amperes. So just remember this basic triangle, that is your base. This one is hypotenuse, this one is perpendicular, sorry, this one is hypotenuse, this one is active power, this one is reactive power, this is apparent power. This one units are kilowatt, this one is kilovolt ampere reactive, and this one are volts amperes. This power is supplied by the source, and these two powers are absorbed by the loads, because load takes active power as well as the reactive power. Now comes towards the load 2. For load 2 we have conditions. For load 2 what is given to us? For load 2 we have given Q2, that is reactive power absorbed by the load. It is given in the problem. It was nothing but 45 kVAR, kilovolt ampere reactive, right? So with the help of this we can with the support of this we can find power factor of load 2 also given to us, 0.8. Similarly we can find sine phi 2. Sine phi 2 is comes out to be 0.6. right? So the apparent power absorbed by load 2 is nothing but the ratio of reactive power over sine phi 2. So all quantities are given to us, right? 45 over 0.6. This one was kVAR. So S2 complex power by load 2 is 75 kVA, kilovolts ampere, complex power by load 2, right? So how you calculate the active power of load 2? You need to just use these relationships. See, if you multiply by apparent power to the cos phi, you will get active power. So in similar fashion, you will get P2 is equals to S2, that is apparent power, times cos phi 2 times cos phi 2, right? So put the values, 75 into 0.8. So you got 60 kilowatt, 60 kilowatt. Therefore, the complex power due to load 2, what is the complex power for due to load 2 is P2 plus of JQ2. So P2 was 60 kilowatt, 60 kilowatt. And what was the reactive power? It was given to us in the problem 45, right? 45 kVAR. So as a whole, the units of this is kilovolts ampere, right? Kilovolts ampere. It was also asked in the question that you need to find the complex real and reactive power absorbed by the combined load. So what you have to do? You have to do just you have to sum up the both the powers, that is S1 plus of S2. You will get the combined real combined apparent power, total complex power absorbed by the load, right? So you need to sum up. When you sum up, as we calculated S1 S2, we already calculated. So just sum up 90 plus of J 85, and the unit are kilovolts ampere. See, S, that is apparent power, complex power, and when you convert into its phasor form, you will get 123.8 angle 43.6 degrees. The units become same, kilovolts amperes, right? So in the final kilovolts ampere, that is the final complex power, comes out to be this. So this one is the angle, that is power factor. If you take cosine of that value, you will get the angle of the combined load, that is 0.727 lagging. So in this case, the real power comes out to be 90 kilowatt and the reactive power comes out to be 85 kVAR, right? Now move towards its second part. Second part is to calculate the line currents. Part B, the line currents. So we know S is equals to, that is apparent power is equals to root 3 times line voltage times line current. And what is line current? If you rearrange this equation, line current is nothing but S over under root 3 times VL. So so rearrange the formula for the line current. Line current is equals to apparent power over under root 3 VL. So apparent power was 50 kVA and line voltage was 240 kVA, 240 kV, sorry, and it being same for both the loads, right? Because the line voltage becomes being same. So line currents comes out to be 120.28 milliamperes for load 1. Since the power factor is lagging, the line current lags the line voltage by, since power factor is lagging, so you can say the your phi 1 is nothing but cos inverse of 0.6. You will get the angle, that is 53 point, sorry, 53.6 13 degrees, right? So you can write as line current IA1 is equals to 120.28, that is magnitude of current, and because it is this is lagging, so minus 53.13, right? So this one is a line 1 current. Similarly for load 2, in the line current that is draws by load 2 is nothing but S2 over under root 3 of V. So S2 was what? 75 kilovolts amperes, kilovolts ampere, 75,000 over under root 3, and it was 2240, right? So the line current 2 comes out to be 180.42 milliamperes, and the line current lags the line voltage by, since it was given to us in the beginning that the power factors are lagging. So we and the power factor for load 2 was 0.8. Power factor for load 2 was 0.8. When you rearrange and you calculate the phi 2, you will get 36 point, and that is phi 2 is cos inverse of this value, that is 0.8. You will get the angle that is 36.87 degree, and how you will write the final, that is the line current by load 2 is the magnitude of the current, that was 180.42, and the angle comes out to be 36 minus, because lagging, minus 36.87 degrees, right? So it was also asked that what is the total line current. So total line current is what? Total line current is the sum of line current from load 1 and line current from load 2. Just sum up these two currents, 120.28 angle minus 53.13 plus 180.42 angle minus 36.87. So you will get 216.5 minus J 204.472. If you convert into its phasor form, 297.8 angle minus 43.36 and milliamperes, right? So this one is the current, total current drawn from the uh, drawn from the source to these two loads. Alternatively, we could obtain the current from total complex power. Another way to calculate this current is also, you have another option, that is total line current is from the total absorbed power, that is S over under root 3 times V. The total power was 123 under root 3 297.82. See, the same current. Okay, this is an alternate method. You can calculate by total apparent power. It was a sum of load 1 and load 2, if you remember, S1, S2, right? If you divided total apparent power by these quantities, you will get the total line current. So this was an alternate method to calculate, right? So if you calculate all the line currents, that is phase B, phase C, and the sequence was ABC. It was given. The phase sequence was ABC. So it comes out to be, that is IA1. We already calculated IA1, that is line 1 current. It was comes out to be 297.82 angle minus 43.36. Similarly, the second line current, that is IB2, having the same magnitude, but the angle, yes student, the angle 297.82, because the second line current is 120 apart from first line current. So minus 43.36 minus 120, so angle becomes minus 163.36, magnitude being same, right? Milliamperes. And what is line current 3? That is third line current, IC2, is again, it is the third line current is 240 apart from the first line current. So when you minus that angle, that is previous angle 163.36, you will get the value 76.64. So third line current, the magnitude being same, that is 297.82, the angle becomes 76.64 degrees. So these are all the line currents. And we end up this problem session with the balanced loads, right? These all problems are related with the balanced star and delta. In next lecture, we will handle it. We will do the problems of unbalanced networks, unbalanced loads. So that's end our lecture.